So let's talk a little bit about engineering notation. It turns out that engineers are just a little bit different than most people, and in particular, although we're quite similar to scientists, we like to do things just a little bit differently than scientists. And being able to represent your numbers, especially in engineering notation, is one of the things that will set you apart as an engineer. Now, really the only difference between engineering notation and scientific notation is that engineering notation, the power of 10, the exponent of 10, is always going to be a multiple of 3. So we would have 10 to the third, 10 to the sixth, 10 to the ninth, and so forth, or 10 to the negative third, 10 to the negative sixth, 10 to the negative ninth. We'll talk about things as small as 10 to the negative 12th, or even 10 to the negative 15th, or even as large as 10 to the 12th or 10 to the 15th. So by using multiples of 3 for our exponents, and then by representing those multiples of 3 with the appropriate prefix. So I don't just talk about coulombs, I don't just talk about farads, I don't just talk about amps, I talk about milliamps, I talk about gigajoules, I put a prefix onto the unit that specifies which power of 10 I'm talking about. So if you do that, it turns out that sometimes just by glancing at the units, you can know whether or not the scale is appropriate for your problem. So for example, if I give you a new cell phone and said, here, this cell phone has several gigabytes of memory. Well, of course, several is pretty flexible there, but as soon as you see gigabytes, you're like, yeah, that's about right for a cell phone. I'm in the right territory. I'm in the right ballpark. But if I said to you, oh, here's a cell phone that has several megabytes of memory, you'd say, no, really, this is going to be useless to me. I suppose I could hold a door open with it, but the scale of the number there is just completely wrong. It doesn't even matter what the word several means. Unless several is 10 million megabytes, then I suppose it's reasonable. But unless the units are correct, unless the prefix in the units are correct, you're pretty much in the wrong ballpark. So you don't even need to look at the exact number. You can just look at the prefix on the unit to see whether or not it's sufficient for your purposes. So here you can see a table, and I've tried to go maybe one or two in each direction further than you might realistically need to know. But you can see here that if we start in the middle, there's no prefix if you're talking about numbers that are on the order of 1. But as you go up to 1,000, it's kilo, mega is a million, giga, and tera. I don't usually tend to see peta or exa very often. There's some discussion about petaflop computing. So here you can see that we might be talking about a quadrillion floating point operations per second. But really, for our purposes, tera is about as high as we're going to tend to go in this class. And then going downward, we have milli, we have micro. Notice that micro uses the Greek letter mu. So that's the only non-English letter that appears here in any of these prefixes. There's nano and pico, and then femto. I do occasionally see things in the range of pico and femto, but most often we would not go down all the way down to atto. And so, if you ever want to win a bar bet, you can maybe memorize more prefixes than these. I think there are yada and octo. There are others that are even higher and lower than these, but really for our purposes, these are the ones you're going to need to know. Notice that the symbols here are almost all capital letters if it's greater than 1, and they are all lowercase letters if you are less than 1. The only exception to that is kilo, which is technically a lowercase k, although I see engineers write that as a capital K quite often. And so if you write a lowercase k, you're specifically correct. If you write a capital K, most people are not going to yell at you for having written it as a capital K. Now, the key to converting the number into engineering notation is that the coefficient, which is to say the digits other than the exponent, have to always be greater than or equal to 1, but less than 1,000. And so, you have a multiple of 3 in the exponent. That means that you can always get the coefficient within the range of strictly less than 1,000, but greater than or equal to 1. And if it's not, if it's less than 1, just shift the decimal place 3 places to the right. If it's greater than 1,000, shift it 3 more places to the left. So here you can see an example. I have 12,550 volts. 12,550 volts. I could write that out as 12.55 times 10 to the third volts, which, because this is written as 10 to the third, I can see that the 10 to the third is going to correspond to a prefix of kilo. So 12.55 volts. And if we're trying to be as careful as we possibly can, then we're going to realize that the 0 here at the end is not strictly significant because I didn't have a decimal point after the number. So I just write this as 12.55, and that way I maintain the same correct number of significant figures. Similarly, I could write out 0.000345. I could write that in scientific notation, 3.45 times 10 to the minus fourth. Or I can divide this number, the 10 to the minus fourth, I can divide that by another 2 powers of 10, divide it by 100. But if I do that to balance, then I have to multiply this number by 2 powers of 10. So it becomes 345 times 10 to the minus sixth amps, and that is 345 microamps. 345 microamps, not very much current, but definitely a current that could be significant in some applications. So my suggestion would be to you to do your best to use engineering notation throughout the assignments and exams for this class. Believe it or not, it will make your life easier, but it'll also help us, the graders and the professors, to quickly verify that your answer is correct.